With the recent advancements in AI and its ability to write code for us, are these software design patterns even necessary then? Is there value in continuing to leverage them, learning them, or even improving their implementation? These are some of the questions that we will try to answer as we explore the use of design patterns in this day and age of AI. Our speaker leads the development of next-generation software as Director for Power and Water Solutions at Emerson. Everyone, please give a warm welcome to Mr. Leo Lim.
Good morning. I hope you guys can hear me. So let me just share my screen. Oops. But yeah, good morning, everyone. Welcome. I hope you can hear me. Let me just quickly check in the chat box. Okay. So, all right. So today we'll be meeting. We'll be discussing all about design patterns. So, by the way, my name is Leo Lim. As based on the introduction, I'm the director for Power and Water Solutions for Emerson. Emerson, we do automation solutions for the different industrial applications. In my case, we are focused on the power generation and water wastewater market and industries. So we here in Manila, we develop a lot of the software that's being used in those industries, and we develop software from ground up. So, which is why this topic is very close to my heart. We have been using design patterns for a while now in many of our applications. But what are design patterns? If you're a developer, for instance, and you keep on having this like deja vu, like you are writing code that you have already used before, or if you are an architect, a software architect, and you see an implementation and you think maybe I can use this in some other application, or if you're a manager, a software development manager, a product manager, and you see that there are cases where you have a complex system that maybe you can break down based on something you've learned in the past, you are probably using design patterns. So formally, design patterns, the way I think about them is really three things. First of all, they came from the object-oriented world, right, in development. So they are object-oriented constructs. So at the heart of an object-oriented environment is really reusability. So this is the same for design patterns. It's really how you reuse some of the codes that you've learned, not really the code, but more of the framework or the lack of a better word, pattern that you use. Basically, they're like templates. They're not really code that you can like reuse like libraries, but more so ideas, right? That you can apply to common problems. So it's really rooted in object-oriented programming. But as you will see later, it's starting to evolve, right? It actually has the inspiration for design patterns come from architecture, and when I say architecture, it's really those of the construction type of things, right? Where you have like your different types of architects use the patterns so that they can name some of the common implementations that they use in designing or constructing a building. So it's the same with code. We give these patterns a name so that you can identify them and you can communicate with your colleagues. So if someone understands what you're talking about when they say, "Oh, I'm implementing a singleton, a factory, a decorator," then you know exactly what your colleague is talking about. In this regard, design patterns really describe how objects or classes in an object-oriented environment communicate and interact in a given context. To me, the second point is they are really like building blocks. Like I mentioned earlier, they're not really part of any library, or maybe you can have like a catalog of design patterns, but they're not really part of any code library. Basically, for me, they're like templates that you can use to build basic block functionality. So you can apply them to very straightforward situations, like in a function, for instance, or in a collection of classes or objects. Or you can use them to build more complex applications, like web applications. So some typical a common framework, for instance, that's popular in these types of applications, like model view model frameworks, right? They're a type of design pattern, so to speak, but more applied towards a larger implementation. So in that regard, they can also be used for whole software architectures, like I mentioned earlier. Maybe a whole software stack, a technology stack, for instance. You can use design patterns as well. And lastly, design patterns, at least for me, in the years that I've used them, is really a discipline. It's part of an engineering workflow. It's how you develop software. So some people, especially if you're new, like me when I was young, when I started development, you really just wanted to solve problems, right, and implement it as fast as you can. But typically, um, the code becomes convoluted, and that's where design patterns come in, because it helps you improve your workflow. If you know these design patterns, then you can do faster coding, you can implement faster prototypes or implementation because you know them in your mind. So it's really capturing knowledge and experience of seasoned software developers and designers. um, so what it does is it's really giving you like a sense of what can I do, what's next, and are there different combinations of classes and objects that are have been used in the past that will help me solve my particular problem. So what people have done is really to collect a catalog, carefully documenting these design patterns, these reusable software implementations. And you will see later on, I put the references at the end of this presentation. There's books around design patterns, machine learning design patterns, and there are tons of articles out there on the web that you can refer to. But basically, those are what design patterns are for me. So they're really practice. It's a discipline. So let me give you an example of a design pattern, one of my favorites. uh, what's called the observer design pattern. This design pattern is really defining a one-to-many relationship between objects. So you can have like one subject object, which is I'll give you an example later on, linked to many observer objects. So if you think about it, in relational database design, right? This is also a pattern that you can see in most database management systems, right? It's having that one table being related to multiple tables, right? One to many relationship in an RDBMS design. So as you can see, these patterns really manifest everywhere, not just software. So you can really apply them to many different things. But the concept really for the observer pattern that I'm discussing here is when there's a change, for instance, in your subject or your main object, all other objects linked to it get updated and notified. So here's an example. It's a very rudimentary illustration that I have here. So suppose you have a table, like maybe an Excel table, right? And then you have values inside them. And then you have maybe another tab which shows a pie chart, another one a bar chart, and then maybe another one an image of some sort, right? So typically, when you update the values in that table, the charts get updated as well if they're linked to that data set, right? So that's a classic example of an observer design pattern where where changes to the main or the subject object affects all the other objects linked to it. So in this case, those are charts. So the charts reflect the values that you enter in your table. In pseudocode, this is how it would look like. You define an observer class, right? And you will have an update function. So when you call the observer class later on, you will invoke the update. So they update themselves basically. And then you have a subject class. The subject class is really, it has a collection or a list of observers. So you can add or remove observers. And then there's a call notify, which basically is a function that when it's invoked, say subject.notify, you go through all the observers in your list and then call the update function. So this essentially abstracts, right? So whatever type of observer that is, as long as it's a subclass of the observer class, then you can call the update function. And then basically, in the case of the example, if it's linked to a set of data, a table, then it's up to the observers to update themselves based on the subject. So this is just a typical example of a design pattern in the traditional world of object-oriented programming. There are many, many more design patterns related to object-oriented programming. You can look them up. But there's really basically three classifications or categories. We have the creational patterns, which are really design patterns that define the common ways of instantiating or creating an object in a system. What it does is these patterns make the process independent. So basically, you have the flexibility of adding more observers, right? As long as they adhere to the interface, like in my example previously, the interface in this case is the update function. So as long as they all have an implementation of the update function, then you can call them each, right? And they execute their own updates. So that's one of uh, the type of abstraction. But don't, sorry, don't get me confused. The sample is not a creational pattern, but that's the level of abstraction that I keep talking about, so that you can make it more flexible. So when you create, for instance, an instance of an object, you can create an observer. You can combine it with the example I mentioned earlier, an observer pattern. So that way, when you create objects, it's not hard coded. Structural patterns, on the other hand, outline the common ways of how you organize your classes. So, like in the example again, I know it's not a structural pattern, but it's composed there's a list of observer objects or classes in the subject, right? So it's a way of composition, right? So you can have different combinations of this composition, and we call them structural patterns. It's really how you organize your objects to create bigger systems. And then lastly, you have the behavioral patterns, which really characterize the interaction of objects in the systems. So the observer pattern earlier I showed you is an example of a behavioral pattern. It's actually defining the flow of information, right? So when a the subject object changes, it it forces all the observers to update themselves. So that's the type of control flow that is typical in a behavioral pattern and defines really how communication of these objects work. So there's tons of catalogs already for all the design patterns. The trick to using design patterns is not applying them all the time. It's really knowing when to apply these design patterns. The trick is applying them when it's necessary, because typically sometimes we tend to apply all design patterns to all problems. It's like a hammer looking for a nail, right? But really, when sometimes you just need a simple straightforward code. So design patterns become useful when it becomes more complex, systems becomes or an implementation becomes more complex, and then maybe that's the time you look at design patterns. And design patterns, they have names, right? They have the purpose and the problem they're trying to solve, and it's really very useful to have a reference to these types of catalogs. So that's the introduction to design patterns. Now let's move on to the next section, which is really the meat of this discussion. So design patterns, like I said, are grounded on object-oriented programming. So do they still have a place in machine learning, or AI workflows. We know that AI now, especially the generative type, can generate code. So what's the place of design patterns in such an environment? Can we still use design patterns? So before I go into that, let's look at the intersection of design patterns and machine learning or AI. So I'm not going to define machine learning or AI here. There's going to be lots of definitions, but really we're just talking about the context of machine learning here and the application thereafter, which is we can call AI. So here in the yellow circle is what we call the uh, traditional or applied AI instances of design patterns. So this is really the traditional software design patterns I was discussing earlier in the section, applied to software applications that leverage machine learning or artificial intelligence. So meaning this is already an application of a machine learning work implementation. So you can uh, in these cases you can still use design patterns because still a software application, right? And then there's the blue circle here, which is really the machine learning or AI engineering. In this case, design patterns are repeatable solutions to commonly recurring problems in an engineering machine learning engineering workflow. So what's the typical workflow or life cycle for machine learning engineering? There's the data preparation, the model building, how you operationalize your models, including deploying them, maintaining them, keeping them relevant, retraining your models, those types of things. So there are also design patterns that you can apply to machine learning or AI engineering workflows. And then lastly, like I mentioned just before this section, it's really leveraging the assistive AI, generative AI, if you will, to do code generation. And that's using machine learning to either detect the design patterns in your code or the applications that can design patterns in your existing code base, or generating design patterns in various contexts. So maybe in your test procedure, maybe in your main source code, right? Leveraging them. So these three areas really is in the middle is the intersection is the design patterns. So there are design patterns that you can use for software that leverage AI. There are design patterns that you can use to engineer an ML solution, and there are design patterns that actually you can leverage using code generated by an assistive type of AI. So that's really the intersection of design patterns, ML, and AI. So let's look at the first area, which is using traditional design patterns for software applications that leverage machine learning and AI. So here you see a sample they call the factory design pattern. Um, as the name suggests, it's a factory, so it creates objects or or instances of these of the different classes. It's a creational design pattern. So it's used to create an object. The factory design pattern is used to create an object, but the object can be a variation of the same class of objects. So let me try to explain that. An example that I try to use when explaining this is, for instance, you're a user of an office type of application, maybe a document creator or something. When you create a document, right, you press new file, new document, and then you choose the type of document. It could be a plain text, HTML, or maybe even a presentation. So that's a classic example of a variation of the same class. The class is document, but you have different variations of that class. That document can be a plain text, can be an HTML, or a presentation. So that's a simple way of explaining what a factory design pattern does. So when you press new, you select template and then press create, it's actually creating an instance of a document class, but of a specific object, right? That could be a more specific type of document. So here in the middle, I have another illustration to help drive this point, but this time more towards the AI side of things, right? Or an ML type of implementation. So when you do a software application that leverages machine learning models, or maybe you pass a prompt to a generative AI like ChatGPT, right? There's going to be data involved, like in any type of application. So in these types of applications, it becomes no different from a traditional database application, right? Or a data application which gets different data from different sources as input to the system. The system in this case being a machine learning model or an AI system, right? So in this case, for instance, if you are going to pass a data source to your model or your system, you can get the data from different sources. It could be a database, it could be a file, it could be an API, a web-based API, for instance. So if you had a data source factory, then the idea with the factory pattern being applied to this type of problem is you can abstract whatever source of data you are getting for, be that a database, a file, and an API, and then you really just provide it as a data source to that model. So the model wouldn't know if whether the data came from a database, a file, or an API. And that's because the data source factory abstracts the creation of your data source based on the different types of sources that you have, that you are able to connect to. So this is a good example of a traditional design pattern applied to a machine learning software implementation. You can see here the pseudocode. Again, I tried to make it very simple, but in reality, design patterns can be as simple as you want or as complex as you need it to be. So for illustration purposes, we use very simple pseudocode. So you can see here, there's really two classes involved when you have a factory design pattern. One is the creator, which creates the product, and the product being another type of design pattern. So in the sample below, the products are the database, the file, the API. Those are the objects of the product class or the instances. And the data source factory is your creator. So if you can see in the creator, there's a function, a procedure create, and then you pass it the ID. But what it really does is when you implement that function, you the create and then you pass the ID, you can have logic inside that function that depending on the ID, you return a different product. And that product is a subclass of the product class. So in this case, we have the my product and your product, which really inherits from the base the base product class. So in the case of the example again, you may have your data source class, and then the database data source, the file data source, and API data source may be um, versions or subclasses of your data source class. So now you can return the class when you call the create function in your creator class, it returns the correct object depending on what you want to create based on the ID in this case. So this is again a good implementation or a sample implementation of a factory design pattern being applied in machine learning context. So now that's the example of a traditional machine learning pattern applied to an AI context. Let's now look at the other bubble, which is really the ML or AI engineering. So this is a typical workflow for a machine learning engineering. When I say engineering, because there are steps involved, right? When you're trying to implement a machine learning or AI type of system. So the start is the data preparation. Again, machine learning needs lots of data, right, to be able to be accurate, to have really good results. And as the name suggests, machine learning is just really a code or algorithms that learn from data. So it needs data to be fed into it to be more accurate. So data is the heart at the heart of machine learning implementations, and preparing data and even understanding the problem domain, which is really the input to your system. Those are critical stages. And there are design patterns that you can use as well, because there are commonly appearing situations in data preparation that can be generalized into specific, like, patterns that you can implement to help you implement your data preparation faster. The next step is the training loop. This is really the process of developing your machine learning models and passing data. So it's an iterative process. When you train your models, typically you have a training data set. So remember, from your data preparation, you prepare a subset of that data for training, and that's where your machine learning model learns. There's also a step of evaluating those results, which is also getting a subset of data from your main data that you prepared, and evaluating if your model is performing as expected. So it's kind of testing it, and you do that in a loop until you get to a point where you are satisfied with the results of your machine learning model. The next step then is what is referred to as serving. And what does serving mean? Serving means, so if you have a model now, what do you do with your model? You deploy it. Just like in applications, after you develop your software applications, maybe your web application, then you deploy it via web server, right? So now it becomes something that's usable by other users, not just by you. So in this case, serving may mean putting it in a cloud infrastructure. Could be a public cloud, could be an on-prem cloud that you use internally, or could be a device, right? Because there are technology stacks available now to support the deployment of machine learning models in your watch, in your tablets, phones. And in the case of Emerson, we call these edge devices, which are really the equipment or devices that are installed down at the plant level, or even your instruments, right? So that's the purpose of serving. And again, there are patterns to make sure that recurring situations when you serve models, uh, you can use well-known or identified architectural implementations to help you make it more efficient. And then lastly, and something that typically when we talk to customers, right, who want machine learning or AI implementation, is really the maintenance. Machine learning AI applications require maintenance just like any other application. So you can't, like, deploy them and then forget about them, because what happens is, as it gets deployed in a production environment, it starts ingesting live data, real-time data, right? And the real-time data over time changes, right, from the types of data you use to train the models. So when that happens, the models need to be retrained on the relevant data to stay updated. So a good example of this is, say you have an AI or ML implementation that aggregates news, right, or knowledge from news articles, whatnot, and then you train it using data from 1990s, for instance. If you deploy it now, it's going to have bad results, basically, because it's trained on data from the 1990s, and instead of the present timeline, right? So in this case, you need to train that model again using articles that are more updated, so that the results are more relevant to today's time. So maintaining models and AI is really a continuous process. And again, there are design patterns that you can use or refer to continue redeploying your AI implementation, making sure they're updated. So these are the four basic steps in an AI engineering. So now let's look at a specific example. This one is called the multi-modal input design pattern. So what's like I said earlier, design patterns are really rooted in object-oriented programming, but they're not limited to just programming. For the machine learning AI workflow engineering, for instance, many of the patterns here, while they do involve some amount of coding, they are also like templates or guidelines, if you will, to solve common problems. So, like in the multi-model input, a typical situation you'd find when you're implementing an machine learning application is that you need to ingest different types of data, right? A good example would be if you have, say, a machine vision type of machine learning implementation and it's getting data from a CCTV, right? What makes it more complete is if it can ingest data around time, date, and time as well, so that it can relate whatever it sees in the video with the date and time and location data. So that you have like a machine learning type of model that contextualizes the images that it sees, right, with date, time, and location. So the modal input is a design pattern that addresses these types of situations. And it does so by concatenating or really generalizing the results. Because, of course, a CCTV data is very different from a date, time, and location data. Date time is date time, location may be coordinates, right? A CCTV is a large type of data. It's also composed of bits and bytes, but if you look at it, it's going to be big. So how do you then uh, concatenate those? So there are really different ways of doing this, but again, uh, I'm going to provide you a very simple example, but again, you can make this as complex as you want. So in this example, we're looking at a review model. This is a machine learning model that ingests reviews from, say, from different restaurants or hotels or whatnot, and then you have like text reviews, right? Whether this is good, this is bad, and then you have a score, one being the lowest and then five being the highest, for instance. And what this review model does is learn from all the data, the good, bad reviews, and score, and then gives you an overall rating, stars, right? 3 stars being the highest, for instance, in this example. So what 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 you need to do here then is to combine the good and bad data and the score data. And you can see here a pseudocode that does just that. Um, First, you define your score, right? 1 to 5. And what you can do here, and when we say concatenate, is you have to have a representation of the good and bad, and as well as the scores. So what you can do here is create an array where you have pairs, right? Good, bad, and then a score. So this is an example of the code there, where you provide the score and then you define good or bad. It returns 1 if the score is lower than 3, 0 if it's greater than 3, or 0 if it's higher. So, and then you process that, and there's a code here that does a for loop, right? And then you basically append the rating with the good or bad data, which is really the 1 or 0. So this is a very simple example that translates, say, the good and bad into a boolean. It can actually be a text. Maybe you apply some other machine learning there to say that it's 1 or 0, but it's really putting them in context with one another. And then you can do this as many times as you want. You can have an array which has multiple variables in it, right? But in this case, it's only two, a bad score. So this is a typical design pattern that you use for multimodal input. Of course, in the example of a CCTV and date, it becomes more complex, right? But again, if you have a basic understanding of the concatenation portion in the multimodal input design pattern, then you can apply it to more complex problems. As with the traditional design patterns, the machine learning engineering design patterns also have categories, and most of the categories are also based on the workflow that I showed earlier. So you have data representation design patterns. These are really design patterns that you can apply to manipulating your data. You also have problem representation design patterns, which are different ways of representing input to machine learning model. A good example that comes to mind is, for instance, when we apply a predictive maintenance type of machine learning for a power plant, for instance, you don't just feed your models all the data. Uh, that's the data representation part, right? But you also need to understand the problem domain, because the plant, a power plant in this case, operates at different power levels, right? It could be operating at 30%, 50%, 70%. And knowing that actually gives you your problem representation, right? You don't feed the all the data for all those operating modes, as we call it, into your models, but you identify them. And those are what we call problem representation. It's how you classify your problems and make it more manageable when you use machine learning models. And of course, there's model training patterns, which really characterize the training loops and the situations that occur frequently that you can use them for. There's also design patterns for resilient serving. I mentioned earlier, serving is really just a term for deploying your models. So how do you make sure that you are efficient in deploying them to a production environment? There are patterns for that as well. And then there are reproducibility design patterns. The the thing with machine learning models, right, is they're not always reproducible, meaning the results, even if you provide the same inputs, you train it with the same data, the output may change, right? And that really means maybe changing your bias parameters and all the stuff like that. But there are design patterns that can help you make your results more reproducible. So these are those types of design patterns. Now, again, I'm not inventing these design patterns. There's a catalog of design patterns. I again, I have references to the books that I referenced, and there's a really good book on design patterns for machine learning. They call it, the book is titled Machine Learning Design Patterns, and I suggest you grab a copy of that book if you want to learn more about these patterns. So we're done with the area where you have your traditional design patterns applied to software applications that leverage machine learning and AI implementations. And then you have your machine learning design patterns for your machine learning engineering workflow. And then the last area is really the assistive or code generation. And in this area, there's really two ways you can leverage design patterns. One is you can use machine learning to detect design patterns. There's a good amount of research going on with this. There's very few uh, papers around discussing this, but I've seen a few, and it's really trying to improve the code by looking at the code and using machine learning to analyze that code to propose or suggest the use of design patterns. What this does is really it helps you improve code quality, code reuse, and simplifies the product evolution. So when we say product evolution, it's really how you upgrade or update your code. And over time, this saves time and money, because as design pattern users know, uh, proper implementation of design patterns actually means better software, because you can, if all the developers, for instance, are speaking the same language, then they can say, oh, this is an observer pattern, and we can use this in the same in a different applications but the same context. And then there's the coding with AI assistance. So I'm sure you've heard about GitHub Copilot now. So they have a patterns implementation, which actually gives suggestions as well on rudimentary design patterns that you can use inside your code. Uh, and again, this really helps with your rapid prototyping. You can quickly generate your code, and you have and generates those design patterns for you. So, like I said earlier, since there's no libraries for design patterns, this is the next best thing. It's like having another person looking at your code and suggesting design patterns. So that's really how far AI has come when it comes to generating code. So going back to the question, are design patterns still relevant? Do you still need to study them? I think they are. Remember, the way I see design pattern is from a knowledge management standpoint. They are not reusable pieces of codes or patterns. They're actually reusable pieces of knowledge. Knowledge that you can use to your software projects, to your complex systems, to your AI or machine learning workflows. Um, Again, we discussed three areas where you can use design patterns, right? The traditional ones, I mean, in the context of AI and machine learning, the traditional ones where you can apply them in software applications that leverage ML or AI, or the new design patterns that are specific for machine learning, AI engineering purposes. And then, of course, how to leverage machine learning themselves to detect and generate those design patterns. So knowing the basics really gives you an upper hand when you develop more complex systems, and those basics are defined by the design patterns. Remember, they are knowledge pieces of knowledge that you can reuse, so that you leverage the learnings from previous generations. When used properly, design patterns can be a very powerful tool in your toolbox. Whether you're a programmer, a designer, an architect, or even a project manager, knowing these design patterns will help you make develop your products more efficiently, and you can generate code more quickly. Again, there's a catalog of design patterns that you can learn and understand. You can check out the I have the references and the sources later at the end of this slide, so you can look at those. They have the typically the pattern documentation has a name, a problem where you apply, and then some sample applications. So they're very useful. So a little bit about Emerson before I end my presentation. So we are a global industrial automation leader. So meaning we provide control system instruments to industrial applications such as power, oil and gas, manufacturing, electronics, those types of things. So we have two general areas of interest, the intelligent devices. So those are the type of edge devices that I tell you. More and more machine learning applications in AI are being pushed down at those levels where you can do rudimentary analysis, right? And then there's the software and control layer, which really does the whole automation thing for, say, a big power plant or maybe a renewable type of system, right? So I work with the Manila organization. Here we do both software and hardware development and testing. So we develop the software from ground up. The products that you see there, Delta V Innovation, we develop them from ground up. And right now we're also developing machine learning and AI solutions for industrial applications. The one I mentioned earlier for the power plants, that's a typical type of solution that we provide to our customers, and our software are used worldwide. So if you have time, please visit our virtual booth so to get to know Emerson better and the things that we do. And if you have any questions, I'll also be hanging out by that booth as well as the lobby. So here are my sources and reference. A very good book, uh, which really started all this, the design patterns, elements of reusable object-oriented software. So you can check that up. And then a new book about machine learning design patterns, solutions to common challenges in data preparation, model building, and ML ops from O'Reilly, and some other resources. So that's it. Thank you. And I'll be accepting questions now.
Okay, thank you, Leo, for your great presentation. However, before we go to the questions, may we please watch this video from Emerson?
Go.
Right, it's nice to see what you do at Emerson with that video. So now we are going to proceed with the questions. Let's start with our first question, which is from Raymond. So, from Raymond, where do I start when I wanted to learn about machine learning AI? What references can I start with? My background is CNET.
Oh, C sharp. Okay. Uh, there's actually tons of references, and I think uh, if you really want to start about machine learning, I guess data science is a good place to start because, like I mentioned, data preparation for models, data preparation is a critical portion of the machine learning engineering workflow. So you can look. There's tons of resources about um data science and stuff like that. In fact, if you have like you can start even playing around with it with if you can get a free account, say from a chat from Chat GPT. Gives really good good answers and maybe some references as well. But there are tons of references in the web, and but a good place to start if you're a programmer and you want to learn uh, and if you want to learn get into the world of AI machine learning, maybe data science is a good place to start.
Okay, so thank you for that, Leo. I hope you had the answer that you wanted, Raymond. So proceed. Let us proceed with the next question. So, from Mark Chris Andalo, what junior mid-level positions or roles we can have or apply with if we want to pursue AI engineer profession?
Again, maybe you want to start with the data portion, like data become a data engineer, right? So typically, when people want to follow a career for AI, they start jumping into the development of the models. But that's really very what I would call very scientific because there's lots of math involved. But if you want to get started, like maybe a junior position, maybe you can start as a data engineer, which is really transforming the data so that it's usable for a machine learning workflow. And then, like with any other software practice, right? You start from the basics and then you move your way up to more complex systems.
All right, so now let's proceed with our next question. So this is from Julian Chris Masangkay. So his question is, can you cite a real life example demonstrating the factory pattern where the AI ML component is involved?
Oh yes, we have an application. We have a solution at Emerson where we provide predictive maintenance, right? Predictive type of applications to our customers. Meaning, when we talk about plants, for instance, it involves large equipment, right? So you would want to be able to predict the maintenance of those systems versus reacting, right? Because typically what happens is if it breaks down, it costs a lot of money. So a good example in what we did in our application is we have developed models, right? Or we allow our customers to develop their own models or digital twin of these equipment. But there's so many tools you can use to develop those models. You can use MATLAB, you can use Python, or you can use other third-party tools. So those tools, if you apply the factory pattern, they're just modeling tools, right? And but different versions of modeling tools. So when you create when in our code, for instance, we are able to instantiate those different models from those different tools because we have a factory pattern. So that's one real life example. So instead of like having one specific implementation for a MATLAB model, for a Python model, or for another model, we use an abstract class model, and then we instantiate the actual models based on what's needed.
Okay, so moving on to our next question. This is from Joselito Jojo Paderes. So the question is, I'm curious to know if ML AI can be used to identify anti-patterns, misapplication of design patterns, example, over-engineered system designs.
Oh, that's a very good point you bring up there. There are what are called anti-patterns. Like I said earlier, typically for something for someone who is just getting into it and part of the learning process is trying to apply design patterns even if there's no need to apply design patterns. And sometimes you end up over engineering. Uh, I think ML AI can be used for that as well. There's it's always a possibility, right? There's very few research papers on this, but I think it can be used because again, machine learning is really just feeding a piece of code, a piece of software data, right? So if you have enough data to say to identify which ones are bad practices and which ones are good, then the application I mentioned earlier, where it identifies design patterns, it could be the same ML implementation, right? But detecting the misuse of design patterns. So I think it's entirely possible as long as you can collect that data.
Okay, so we have another question here from Jim Zandueta. So the question is, any advice how one can help the team adopt a design pattern for the organization or a specific project?
Um, like I said, it takes experience. It's not easy, but like any endeavor, you just take the first steps. So maybe a good first step would be to look at all the catalogs of design patterns, right? And you will, I'm sure you will be familiar with some of the technology stacks. Most of them use design patterns anyway. Like I know back in the day when I was using Visual Studio, it was the document document type of design pattern. Then now you have your MVC, model view controller, you have your MVVM. Those are the typical design patterns, and it's really hard. It takes experience to know them, but a good start would be looking at the catalog and maybe using something like Copilot to help you get started identifying those patterns.
Okay, I hope that answered your question, Jim. So moving on, we have another question which is from Ariane May. And her question is, hi, what are the usual prediction models do you use for machine learning?
Well, in our case, it's mostly regression. in a power plant setting, in industrial setting, for instance, you have what you call historian. We in the industry, we typically joke we've been digitalizing data for very much longer than other industries, because we have instruments, right, that gather temperature, pressure, flow, etc., and they're already digitized, and typically they get stored in what we call a historian, which keeps a record of all those variables throughout the plant. And since we have the historical data, and then we have the domain knowledge, which is an important portion of any machine learning activity or implementation as well. We leverage that, and we typically apply regression type of modeling to be able to predict, because once you know those trends and whatnot, then from historical data, then you can project them forward to make educated guesses, so to speak.
All right. So let's go to our next question, which is from Yen Lasaka. So the question is it recommended to apply the sign pattern every time? Are there instances where applying the sign pattern makes your code less efficient?
Yeah, it's not recommended to apply design patterns every time. Like I said, uh, anti-patterns result from the application of design patterns to problems that do not require them at all. Like for instance, a very straightforward. I think design patterns apply when there are many objects involved, because really design pattern is the how these objects interact, communicate, how they're structured. So whenever you start having those types of problems, then that's a good cue for you to start looking at design patterns to make them more efficient. But if it's really just a few objects involved, maybe one or two, then maybe it's not a good place to start using design patterns for.
All right. So again, with the next question. This is from Miss Ariane Olet. So how do you handle prediction errors? What metrics do you use to determine tolerance level for encountered errors?
Uh, in the application I mentioned earlier, where we do predictive maintenance, we have like I forget the industry term that we use, but there's a like a deviation from the expected, from the predicted values, and typically when that happens, we try to tweak the parameters of the model, what they call the hyperparameters. Like for example, the window, the size of the window that the model processes, right? Because in reality, it's really slicing up the data into different windows. Um, yeah, we try to look at those the discrepancy and how frequently those happen, the false positives, right? Where it's saying that it's gonna fail when it's actually not, right? So those are the things we look out for when we try to improve our models. And again, you can only do that if you have some level of domain knowledge, right? Because how would you know that the prediction is wrong if you don't know anything about how the equipment works? And that's typical of machine learning implementation as well. For any industry.
So, okay. Thank you, Theo. So, another question. This is from Christian Ian. So, the question is: are there any emerging design patterns specific to AI ML that developers should be aware of to create efficient and maintainable systems?
Uh, I'm sure there are, because I can create my own patterns if I wanted to, right? But but I think it would be a good place to start looking at some of the already documented ones. Again, the book on the machine learning design patterns is a good place to start. They have some very good insights there about some of the patterns related to AI ML workflow. I think that's always a good place to start. um, they're fairly new, so I think you can consider them some of them emerging, and I think as we progress with the advancements and maturity of AI machine learning, I think there's going to be more.
Okay, so let's move on to, I think, the last question. So this is from Tuesday May Cabido. So the question is, how did you verify, test the efficiency of the pattern that you have implemented?
Well, is it first of all solving the problem that you have? The measure or the stick I use to measure the efficiency of an implementation of a pattern is it easier to maintain afterwards, right? So if I wanted to add a new object, for instance, do I need to rewrite the whole pattern or I just create the object, right? I think that's a good measure of the efficiency of an implementation of a pattern is really how easy it is to extend your initial implementation without rewriting the whole thing, right? So again, because at the heart of design patterns is reusability. So how well you implement it is how well you can extend it is a good indication of your implementation.
Okay, so that's all our questions. So thank you again, Leo Lim, for answering the questions. So now, if you still have more questions, you may chat with our speaker sa Airmeet po in the lounge. So
I'll be in the
that's
lounge, yeah.
yes. So that's all the time we have for the session. So again, let's thank Leo Lim by clicking on the heart and the clapping emojis. But one more thing before I let you go, may we please have a quick photo op? So a photo op. So just smile at your camera and our tech team will capture. So I'll turn off the camera. All right, thank you. You may now exit this session and click on the next. Bye.
Thank you, everyone.